two forms of the synthesis. Now, second type of reaction we talked about. Second type of reaction we talked about was what, guys? Decomposition. So synthesis, your general form, you have your two types. You're writing this down, looking at your notes for reference. Decomposition, how many types were there? There were 4 styles of that decomposition. But really, the general form of a decomposition is what? Say again? Yes, one compound breaking into 2. So decomposition means to decompose, break apart, dissociate. There's a lot of ways to kind of think about that. So if synthesis was 2 to 1, decomposition we could write as 1 to 2. And actually, 2 of those decomposition styles are actually just the opposite of synthesis. So take a couple minutes to look back at your old notes, because I know I'm sure that you've been looking at them probably as extensively as I would have liked to. I'm leaving on the board what I was looking for you, or what I'm looking at from the global perspective. If you are here, there's a video that's been waiting on you since Thursday to watch. Yeah. You guys know it's your responsibility to watch the videos, and if you don't watch the videos, you're gonna be lost in class, because I don't always review with you the next day. And I do have a couple things we're going to revisit from earlier, maybe a week ago or so, called Set 10 related information. And our nomenclature some more. Keep revisiting that, because I graded your quest most of the way, and you guys need some help. You need to watch the notes. You can either do it right now and then watch these notes later. What's the best for you? You can also watch them during intervention. Jamie. Oh, yay! Put those right there.
I know this is awkward, but and then I'm upstairs.
Bye, really. You can watch during intervention too. So we have like 30 minutes, and it won't take. It's not that long. Probably work with the people next to you to grab some notes from them for the moment to get a hang of this. We're not going to be here much longer though, because we only went through 2 styles. I'm going to do a couple examples with you guys. Those examples can go in your notes, like in a written form within your notebook paper notes or on your foldable. Kind of depends on how beautified you want to make it and how cluttered you want to make it. You can see I'm a cluttered person. Like, hey, can I clean my room some though? No one mentioned that? Thanks, guys. Hope to see you guys notice the little things. All right, if you are done, I want you guys to start trying these two reactions, actually, these three reactions. Alright, so finish what you're writing. I understand that you're probably not quite done with the composition. Some of you guys are. You were able to jump on that quickly. And then eyes up here in 5, 4, 3, 2, 1. Eyes on the board. Okay, everybody should be able to look at those reactants and recognize there are two reactants, right? And it's a singular reactant, like hydrogen, which is a singular element, and chlorine, which is another singular element. What are they going to have to do? They're going to have to synthesize. They are going to have to combine together. So this is recognized. You should be recognizing, as we kind of get going here, synthesis versus decomposition. After that, if we feel good with that, we're going to hit the other three, because those are actually much more easier to see. It's just the combustion one's going to require us to learn a little bit of organic nomenclature before we get going. So how do I write hydrogen, guys? Woo! Hydrogen diatomic, right? If it's by itself, it's not really by itself. It's diatomic. How to write chlorine? Cl2, yeah, because we have those 7 diatomics, which are hydrogen and who else? Hydrogen, and where does it start on the other side? Nitrogen? Is that your phone or my phone? Okay, thank you. Sorry, I think we have the same alarm. Okay. All right, so nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are the 7 diatomics. If they're singular by themselves, they're really not. They're diatomic in nature. So as I combine them, when I'm making a new compound, I have to crisscross charges if it's what kind of compound? If it's ionic, okay? And in this case, it's not ionic really, it's 2 nonmetals, but remember how H in the front means acid? Acids are also the ones that we crisscross charges with. So I bring H over here, and I bring chlorine over here. Those are my 2 compounds, and I need to crisscross their charges. What's hydrogen's charge? 1 plus because it's in group 1. What's chlorine's charge? 1 minus because it's in group 7. Crisscross, we have it done already. Now I need to balance it. So what do I need to do to balance? 2 coefficient, right? Because once I make my compound perfect, I don't want to add subscripts there because it's already good. So I just need to add a coefficient to make sure it's balanced. Okay, done. Synthesis. Barium oxide. Ready when you are. Why BAO off the bat? Okay.
And the charges are split too.
They both happen to be 2, right? So she didn't just say BAO, she saw barium and oxygen. She actually did the crisscrossing in her head and crisscross. Barium's in group 2, 2 plus charge. Oxygen's in group. Look up here on the table. 6, and it gets a 2 minus charge. Crisscross, reduce, BAO plus water. Okay? Water is just generic H2O. What does it make, Frank? What do metal oxides, which is this metal oxide here, plus water make for synthesis?
Metal hydroxide.
Okay, so what metal hydroxide will I be making here? Barium hydroxide. Okay, so it's nice to sometimes think about the name and they go, okay, barium hydroxide, ionic or covalent. So I will crisscross charges. Okay, so crisscross and tell me what I get here. OH in parentheses because right, barium is a 2 charge and hydroxide has a 1 negative charge. Crisscross. Okay, so then how many do I need to balance this? Is it balanced, yay or nay? Yay or nay? I heard like 2 yays. How many bariums are on each side? 1. 1 barium here, 1 barium here. Good. How many oxygens on each side? 2. 1, 2. And then that 2 distributes in 2. So we're good here. And then how many hydrogens? 2 on this side, and then that distributes inward as well. That's 2. So it is balanced. It happens to be a 1 to 1 to 1 ratio. Beautiful. Okay, you guys did the last one. These are examples you should be writing down for your own purposes. Ashton, what are you writing down? Zn. And if I had to put a state of matter here, what would I likely put for zinc? Thanks, Ashton. Good job. Solid, because it's a metal, and most time metals are solid at room temperature. Okay? That's just me making sure you guys remember some of your states of matter. And then how do I write iodine? Plus I2, because it is a diatomic, and you have to write it diatomically because it's in the big 7. Because it's by itself, it's not really by itself. Okay, Isabella, when I bring these together, what do I have to do? Because it's what kind of compound? It is ionic. So what's the charge of zinc? Because it's not up here, it's in your head. Say again? How do you know? Zinc always has charge 2 no matter what, and that's one thing we kind of work on as well. So Zn has a 2 plus charge. What about iodine? -1. Crisscross, what do you get? Right. Though it looks like we just said, smush them together, call it a day, we're done. That's what it looks like, right? We did not do that. We actually did use our crisscross rules and then crisscrossed our charges. And that happens there to be balanced as it is. Okay? 1 to 1 to 1. All right, so those are your syntheses examples. Let's do a couple more. Decomposition, forgive me, I'm going to scooch through a couple more that are just kind of redundant in this case. So we'll come back to some of these more interesting ones with synthesis. These were your decomposition notes. You guys already have those down for yourself. Let's do sodium carbonate. Actually, no, I think I did that in my other examples. Hold on. Let's do this one. Magnesium chloride. So, sorry, John, what's magnesium chloride? Hold on, chloride. That's just from the PTOE. And so Cl, that's a good start, not all the way. Look at your periodic table. This is all MgCl2. Where's the 2 coming from? Right, so you're still thinking ionic in this case. Mg2, Cl1, crisscross, MgCl2. And it doesn't have anything else reacting with it, right? So you can already assume that you write the yields arrow. So what kind of reaction is this? Decomposition off the bat, because it's one thing breaking into many things. So now you have to think, okay, what could this break into? If I had to label this to me is binary. Binary things break into its 2 elements. Just the 2 elements. No charges, nothing crazy. How does magnesium exist in nature? It's not a trick question, yeah. And so you give me the state, or just how does it look? It's a solid, it's just Mg, right? It's Mg solid. It's not an ion charge, it's not diatomic, it's a singular monatomic atom. And how does chlorine look in nature? Say again? That is diatomic, right? And that happens to look like I just broke it apart and threw it out together. But this is diatomic in nature, that's why this 2 is here. And this happens to be a gas, like a diatomic gas. So, quick reminders here. Where did this 2 come from? The fact that it's diatomic, okay? Where did this 2 come from? Yeah, crisscrossing charges. Those 2s look like they're the same thing, we just carried it over, but they're not. So remember, there are rules in play here, even if it doesn't quite look like it. All right, Syrian, next one. Calcium hydroxide. I'm ready.
Oh, sorry.
Spell it out for me.
Oh, wait.
Mm-hmm.
And then it'll be 2.
Parentheses 2. Okay, cool. So calcium hydroxide, that 2 came from?
No,
Calcium starch hydroxide is a 1. And so since it doesn't have anything else, I'm assuming it's breaking down. So as it breaks down, this is on your decomposition notes. How do metal hydroxides break down? Jacob, look at your decomposition notes. So how does a metal hydroxide, this is calcium hydroxide, metal hydroxide break down? Metal oxide and what? And water. Okay, so this is going to break it down to a metal oxide and water. Okay, well, we know one of the products, right? Water. Let's just write water first. That gets me halfway there. So, guys, what's the metal oxide in this case? Well, it's calcium oxide, right? So just remember, you know the metal is the first one here, so it's calcium oxide. How do I write calcium oxide? CaO, only because calcium had a 2, oxygen had a 2, crisscross, and reduced down to 1. So it was Ca2O2, but we're reduced down to 1s. And then, is this balanced?
Yeah.
Yes, it happens to be. All right, so I did that for you guys on Friday. I'm going to scooch back to do another couple that are a little bit more complex than this. Okay, so you guys have your rules in front of you. You guys do, yeah, do all those, 1, 2, 3, decomposition ones. I want to make sure that your crisscrossing starts when you're supposed to be. You can kind of reference your notes, because your notes are kind of your lifeline for this first part of this unit. If you don't have your polys memorized, you pull out your poly sheet, because you shouldn't just be guessing at this point. First one, go to the second one. There's 3 up there. I'm hoping you should have had enough time for aluminum chlorate. So let's talk about that one for a second and then I'll leave it alone. Aluminum chlorate, ionic, right? Normal, like binary ionic or ternary ionic? Ternary, because it's got a what in it? Polyatomic, chlorate, right? So I hate chlorate, the polyatomics. You have to know them. You have to know them from in your mind at this point. I'm not like pulling back on that, because this is going to be, this is really going to help you expedite your work and kind of get into the new stuff versus kind of keep refreshing your mind of the old stuff. So chlorate is what, guys? 3 charge, 1 minus. What's aluminum? When it forms an ion charge, yeah. 3 plus. Crisscross, what do you get? 3, good. So you're taking chlorate, you're popping the 1 down here next to aluminum, doesn't look like anything. 3's outside with your crisscrossing of aluminum's charge over. Decomposes, right? And so we could even put like a little triangle on the top and say, oh, it's heated to decompose, or catalyst. I mean, there's some other descriptions we could add there. So what do chlorates always break down to form? Metal chlorides and oxygen. So I told you guys a lot of times the decomposition reactions, many times they make gases. So like our carbonates make carbon dioxide. Our chlorates, we want to say make chlorine, but that would kill us all. So we make the friendly gas, oxygen. So I know oxygen is going to be produced. I'm going to put it right here because it doesn't have to be in the same order. So oxygen will be one thing that will be produced. And then I heard metal chloride. This is the easy one. This is the one straight off the periodic table. So who's the metal? Aluminum. So it makes aluminum chloride. So how to write aluminum chloride? 3, because aluminum still has a 3 charge, chlorine still has a -1 charge, crisscross AlCl3. You do have to crisscross charges most of the time. So we crisscross charges here. That's just a diatomic molecule. We crisscross charges here. So if you're not crisscrossing charges, double check that you're not neglecting that. And then balance it. What do I need to do? So if I add a 3 in front of the O2, what does that do for me? That gives me 6 oxygens where I have 9 over here. Okay, so let's pause for a minute. Do I have the same number of aluminums? Yeah, I'm good. Chlorines? 3 chlorines, 3 chlorines. Okay, so then how would I make 2 turn into 9? Say again? Okay, so now you're telling me, I just heard somebody else say it too. These come in multiple, so I'm going to put the 2 out. So this 2 and this 9 can't equal each other, so I have to multiply them by their opposites. So the 2 is going to come out here to multiply all the way across. So I'm just going to only start with oxygen. So 2 times 3 times 3. 18. Okay, so that's 9 times 2 is 18. How do I get 18 oxygens here? Put a 9 here. Okay, so oxygens are good. Let's look at aluminums. How many aluminums do I have? 2 here. Okay, so what do I need over here? Or 2 in the front. Okay, so that gives me 2 aluminums, 18 oxygens. I'm good. How about chlorines? How many? 6. So 3 times the 2, 6, and then over here I have to already fix it as well. 6. So that was a little bit more interesting with our balancing. Okay, continue. Yeah. I did 9 and 2. Yeah. Because that's really all you can do there. Okay. Well, you guys we can work through a couple of these together. Irie, what's potassium oxide? K2O. So where did the 2 come from? Oxygen crisscrossing over. So you see your charges. You have to make sure that you're using them. Decomposes. So of our 4 types of decomposition, we have binary decomp, we have metal hydroxide decomp, carbonate decomp, and chlorate decomp. Which is this one? This is a metal oxide. I would just call this one binary because it's metal hydroxide you're looking for the decomposition. So, metal oxide, I was going to be metal oxide. Binary decomposes into the 2 elements that it is comprised of. What's element 1? Potassium. Potassium. Done. Okay, what's element 2? Oxygen. Is that oxygen? O2. You do have to make sure that when it's by its singleton sulfate, you write it diatomically. Balance it. Need a 2 in front of which one? I'll put it right here. Okay. And then I have, so there's 1 oxygen here and there's 2 there. So if I put a 2 over here, that gives me 2 oxygens good, 2 oxygens good. But now I have 4 potassium, so 4 potassiums. There we go. Because you will have to revisit to make sure that your coefficients are correct. Okay, good. Potassium carbonate decomposes. Who can give me potassium carbonate? Caleb, start me out. I know you weren't here, but you got me. Say again? Yeah, but I just heard from him. I'm tired of hearing from him. Get me started. He'll pick up. K CO 3. Good job. What's the charge of carbonate? What's the charge of carbonate? -2. So the 2 was here. I crisscross it down here. What's the charge of potassium? 1. Beautiful. Good job, Caleb. Okay, so there's our potassium carbonate. Done. Carbonates decompose to form what gas? Carbonates form carbon dioxide. Okay, so binaries, they break into their 2 elements. Metal hydroxides break into form water, which is likely going to be forming steam. So I think water is the gas from metal hydroxides. Carbonates make carbon dioxide. So let's go ahead and write out carbon dioxide. How do you write that? CO2. And like we wrote in this one, chlorates make, not chlorine, oxygen. Oh, oxygen gas is our friendly gas. Okay. So carbonates make carbon dioxide. Done. Then the other thing that's left over is a metal oxide. Okay, so who's the metal? Potassium. So I make potassium oxide, which is K2O, because K 1 plus oxygen, 2 minus crisscross K2O. Balanced? Yes. Good. Okay. All right, so those are your synthesis and decomp examples from last week we didn't get to do. So take another minute. I'm going to give you guys the notes for single replacement to write down like your little information on your foldable or in your notes, whichever way. I thought the foldable would be a nice change of pace for you to give some variety to your notes. I have this stuff right here on paper. I'll give you guys in a couple minutes. And then I'm going out of order today, so forgive me. Single replacement. Write down this right here. That's your kind of basic information, then your general form, and I'll give you guys an example of that in a second. Today is Miss Inla talks more than she wants to do. I'm sorry. So, you guys have written down your basic information with cations and anions and replacing and things like that. Who can tell me why you think this is called a single replacement reaction? This what? One thing is being replaced. What do you mean one thing? Either the cation is replaced by a cation or an anion is replaced by an anion. Just one thing does a switcheroo. Not double, not both of them, but just one will do a switcheroo. So this first example here and the second example here give those examples as cation being replaced versus anion being replaced. Well, why is A the cation? I mean, sorry, not A. Let's go with B. So what is A replacing in this general form? Who's it switching with? Switching places with B, right? So A and B just do a little switch. And so why can't A move around with C? It's because when you have a cation, where's the cation always written in a formula? The beginning or the second one? The first one or the second one? First one. It's always the first element in a, or I'll say first ion, not even element, because that's a little bit misleading. It's the first ion in a compound, so that's why it replaces B and not C. However, when you look down here, what are you looking at A switching around with? A is switching with C, and so B stays in place, and so A switches with C or replaces C, and that's because the anion is always the second ion or the second element in a combination like this, an ionic compound. So that just gives you a little bit of review what does cation and anion mean. And what does cation mean again? It's the one with a charge of what? Positive charge, and the anion is the negative charge. Okay, so I need a couple volunteers. Volunteers. I need 3 people. Let's go, Brandon. Not everyone's Frank. Oh, great. And Lauren, let's go. Come on, stand up here for me. Look at all this wonderful space I left for you. Okay, so I need you guys to make copper 2 chloride. Sodium, you're by yourself. Copper 2 chloride. So sodium standing to the side. Sodium, cover up your ion charge. Okay, so we have this solid sodium, right? And we have this copper 2 chloride, and they're going to react. So who should sodium replace? Who's he going to switch to? Copper, okay. React! React! Okay, and Lauren just stood there looking pretty. Because all that's going to happen is the 2 cations change places, right? Okay, so now copper is out by itself, and sodium can uncover your charge. Sodium will crisscross, and copper you're by yourself. So put your cover up your charge. Cover up your charge. No, like face flush. Yep, perfect. Okay, this simple solid, right? So this solid will kind of precipitate a reaction. This one will combine over here. So now if I'm like this, you guys read the little part that says a free element must be more active than the metal in the compound. Will this reaction happen? If I told you the first one happened, for sure, the free element of sodium happened. Maybe this one doesn't. Okay, so let's come back to our seats for a second and let's look at our activity series. So, Brandon cannot replace Frank at this point anymore because of the rules of chemistry. So turn the back of your blue sheet, I'll take this from you, okay? Back of your blue sheet, and look where it says activity series of halogens on the upper right-hand side, and then activity series of metals. There should be a number of blue sheets around. Is there one with a surplus? Is that a surplus of blue? Oh my gosh. Guys, we hit the mother load. Right here. Alright, so you guys look at the activities for a hot second while I pass these out to my crew. Who else needs a blue sheet? I guess we share. We'll bite you. Share for a minute. Pass them back to Avery. Actually, one. Okay, so back there you see your activity series. So who's at the very top of the metal activity series? Very top of the metal activity series. Li. Lithium, okay? Group 1, lithium. Who's at the very bottom? AU. Silver. I mean gold. Gold. So at that point, you can kind of see there's some differences in reactivity. So what I mean by the free element must be more active, this basically means more reactive. And more reactive means at the top of the series. Top of this series here. And I will always give you the activity series, I promise, but I won't give you the whole sheet because it's got the polyatomics on it. I know you see that, right? Okay? So I'll give you the activity series only for single replacement reactions. So if the sodium was free, where's sodium at compared to copper here? So sodium's higher, copper's lower. So my example for you is that, you know what? Sometimes, you know, girls, we have some choices, right? So if we're C right here, we're like, do I want B or do I want A? Do I want B or do I want A? I'm with B right now, but I'm cool. Let A and B switch, let it react. But I'm only going to do that if he's super smart and super nice. Okay? Not because he's like a football player or something, I don't know. So I'm only going to do that if it's quality stuff that I'm switching for. Okay? I'm not just going to, I mean, I'm looking for chocolates and flowers. I got high standards here, okay? So we're going to look for A to be top on the activity series, top on the list to do the switch. So what if I was paired with, let's see here, let's say I was aluminum plus magnesium chloride. And I'm chlorine, okay? That's me. I'm right here, I'm with magnesium. Magnesium's pretty cute. Would I want to switch with aluminum? I mean, would I want magnesium and aluminum to switch? Nah, why? Hot stuff right here, okay? Hot stuff, not hot stuff. Why not hot stuff? No, low on the activity series. Okay, I'm not materialistic over here. So we're looking for smarts and brains. So this right here is low in the activity series. So not going to switch. This is higher on the activity series. That's why I'm going to stay combined with magnesium in that case. All right, so let's look at some real examples here, okay? So there's your activity series. I'll go through the halogen one in just a second. That's one I have not hit yet. All right, so calcium plus water, zinc plus hydrochloric acid, and we'll get to this one in a second. Start with these, write down your reactants. I'll give you a tip on this. There's some little arrows that drop from the top to the bottom. They give you some indication of like what kind of things they can react with as well, like hot water, steam, cold water, hydrogen, oxygen from oxides, and so forth. So we're really just using this tool, because the tool gives us all the answers. So calcium plus water, give me the reactants. Ca plus H2O. Okay, so now we're going to go back to the activity series, which is on my back slide. So where's calcium at here? Top-ish area. Okay, so right here. Is this calcium in the arrow that says replaces the hydrogen from water? Replaces the hydrogen from cold water, right? And hydrogen from steam, which aka water, right? It's just hot water. And from acid. So calcium's going to do some damage, and it's going to make this react. So when this reacts, it's already telling you what's one of the products. When it says replaces the hydrogen from water. Who gets set free? Hydrogen, but how do we write hydrogen? H2. So we know one of the products is the hydrogen that's being replaced from water. And you know, I'm going to write water a little differently, because I think this will make more sense to you. Let's write water instead of H2O. H-O-H. Write it like that for me for right now. Because I want you to see that one of the hydrogens is actually inside as a hydroxide, and one is a hydrogen in itself. So who does the switch? Calcium and the first hydrogen here. So they switch. So then H gets set free like this. H2 diatomic. And calcium gets to kind of cuddle up with who? Hydroxide, like this. Wait. Hold on. So how do I determine the number out here? Crisscross charges. I'm always crisscrossing charges, like a boss. So calcium's 2 plus, or hydroxide 1 plus, or 1 minus, crisscross, and 2. Okay, so all I did was a single replacement. Calcium switched with the thing that could form the cation, which is the H plus in this case. Did a switch. Hydrogen got booted out to the cold. Hydrogen had to form a diatomic because that's just how it is. And then calcium had to crisscross charges with what the remainder was, which was hydroxide. Is it balanced? No. What do I need to do? 2 in front of what? In front of the water, right there. 2 coefficient. That's 2 H's, 2 H's. 2 hydroxides, because it gets distributed out. 2 hydroxides. Done. Okay, so that's our one form of a single replacement reaction where we have the replacement within the water form. How about within hydrochloric acid? What are the reactants? Hold on, reactants. Zn plus HCl, hydrochloric acid is binary acid, H with one other non-metal, which is chlor. Chloric is chlorine. Okay, so chlorine is Cl. 1 plus 1 minus crisscross, we're done? Okay, so there's our reactants. Are you starting to see how the patterns look? If you got a single one and then a combined one, so a single element and a compound, that has to be a single replacement reaction, because in this case, zinc's like, I want to get with chlorine. I really want to, but is it active enough? Is it cute enough? Whatever you want to say. So look at zinc right here. Where's the acid arrow at? The third one, so it goes 1, 2, 3, all the way down here. So is zinc within the realm to replace the hydrogen from acids? Certainly is. So zinc's like, get out of here, hydrogen. And what does hydrogen form? H2. So zinc and hydrogen switch places in their single replacement reaction. So zinc boots hydrogen out to the cold like this, H2 diatomic, and zinc gets with who? So zinc gets with chlorine like this. What's wrong? Why is there 2 out here? Crisscross charges. Okay. So zinc does gets a metal, it will crisscross charges. Is it balanced? No, so what do I need? So I see there's 2 over here, hydrogen and chlorine, so I'm going to put a 2 right here in front to distribute all the way out. Alright, so far everything has happened. What if I gave you copper plus sodium chloride? And I'm going to tell you that this is copper 2 plus if it were to form an ion. Look on your or look on your activity series. Is the free one active enough? Why? Yeah, copper's down here, sodium's way up here, so we're looking at copper way down here, sodium's way up here. Sodium's like, I'm the active one. I'm going to get with chlorine. Copper, you're out in the cold still. So what would we write here? We would say, okay, not going to happen, not active enough. It's kind of our reasoning. So if you're not active enough, we just put no reaction. Because it's just not going to react. It's not active enough to force the reaction to occur. And so you can put NR for that for short if you'd rather. Just because it's not active enough. That's what we do. All right, write out your bromine plus potassium iodide example. So what are you guys writing for bromine? Br what? Br2 diatomic, remember, by itself it's still diatomic. Potassium iodide is K. So this is potassium with a +1 charge. Iodine has a I with a 1 minus. This is an ion form. Crisscross, what do you get? Ki. Okay, so in this case, I've got bromine, that's the free guy. So bromine. You look on that metal chart, you'll never find bromine, right? Because it's not a metal. So look right above it. So you're on the activity series, look right above it. This is activity series of halogens. Do you see that? Okay, so we're looking for the halogen here. We're looking for is bromine higher or lower than who? Iodine, right? We're looking at these 2 as a comparison, not the cation in this case, is the anion example. So is bromine more active or less active than iodine? More, because bromine's where on the activity series? High. So bromine is more active because it's higher. So it's like, get out of here, iodine. I'm getting with potassium. So then who's set out by themselves in the cold? Pour iodine like this. At least it's got a diatomic with it, right? At least it's got diatomic iodine. And then how to write Br and K together? KBr, right? Because I don't want to write BRK because that just looks stupid. And you always write the cation first, anion second. Okay, so K1 plus, Br1 minus, crisscross, the ones are gone, and we have our final. Is it balanced? No. Bound with. So I need a 2 in front of the KBr, so that gives me 2 bromines, because I had 2 bromines over there, and, ooh, but I got 2 Ks, so then, I'm going to put a 2 in front of the KI to give me 2 potassiums and 2 iodines. Balancing is the easy part for you guys. We're going to keep on predicting products. All right, let me pause for a minute. So that's single, I already said synthesis, decomposition, single replacement, which is the easiest so far. Synthesis. What about single? I mean, there's one free one. You look and say, is it high or low? If it's high, replace. If not, don't do it. This is the only one you get no reaction on, so that's kind of nice. All right, so that's what those right there are, right? So take a couple minutes and do 1, 2. Start with those 2. Ooh, and 3. 1, 2, and 3, and I'll speech down for you in a second. Which other polyatomic you still know those? Ansley, give me a start on zinc phosphate. Three, because that's going to be what's phosphate? P-O. It's the only one, really. Actually, there's two like this. 4, charge of phosphate. 3 minus. Xenon gets a charge of, zinc always gets a what, guys? 2, crisscross, what do you get? Xenon 3. PO4, 2. Okay, so we have some help there. That's zinc phosphate. Continue, Ainsley. Magnesium. Just Mg. Okay. So your table, tell me what two things are we looking at for comparison for the zinc replacement? Your table.
Oh, magnesium.
Why magnesium and zinc? They're the two cations or metals in this case. So zinc and magnesium. So who's higher? Table. Magnesium. So magnesium's like, hey boo, hey, I'm gonna give it phosphate. Zinc, you get booted out to the cold. So zinc gets booted as just plain old zinc, solid, non-element or just elemental form, and magnesium gets with who? Phosphate to make magnesium phosphate. Go ahead. Mg3, PO4, 2. Where's this 3 coming from? Charged phosphate. 2 coming from? Magnesium. Is it balanced? No. Okay. Ready when you are. 3 on the singular magnesium, and so that gives me 3 and 3. Okay. 3 zincs on the product side, so 3 zincs, 3 zincs. Huh? Phosphate's good. Yep. Yeah. Anybody else have a question on this one right here? So I've switched it up on you, so you'd have to consider the compound versus the element second. All right, last one. Let's do this one together. Aluminum. Al plus iron 3 chloride. Fe. Cl. Chlorine's just chloride. 3. Okay. Who are you looking at comparison-wise? Fe and the free one, aluminum, because those are metals and metals. So who's higher, aluminum or iron? Aluminum, so it's like, get out of here, iron. Switcheroo. Switch, what do you get? Fe is about out by itself. What's up? What's up? I did right here. Oh. See right there, iron 3, switched to down there. Oh, didn't see it. Sorry, no, chlorine. So iron gets booted out, it's a solid form, and then aluminum gets with chlorine to form aluminum Cl3 coming from what? Crisscross charging. Okay, just making sure we're not just carrying the 3 with us, like, let's go chlorine, take your 3 with you. Nope, this 3 came from iron 3 plus charge, and this 3 came from aluminum 3 plus charge. Okay? Alright, so let me pause there for a minute, let you guys can observe some of that. I want you guys to talk in your group about one thing you're going to try different this semester, or this quarter, to keep up your success in chemistry. Good. Anybody? Hold yourselves accountable within your groups. Alright, now tell them what you're doing for your choices assignment due Thursday. Now tell them what you're doing for your choices assignment Thursday. All right, and pause. Write down what's on the board for double replacement. I'm coming here for questions. What's up? So this one, I'm leaving the presentation like product aspect of it. You can do it on a poster. You can do it. You can submit it to me directly. However, it is infographic. If you do like a Q&A with slides and stuff, are you doing it? Yeah. In person. So I would write down like the major points. I need to look though. I wrote down one thing. You had to write down like a reflection.
So like, it can literally just be Q&A on a poster, just have to be like,
And then maybe like jazz it up a little bit, so it's not just written words.
okay, the picture just.
So you're not tweeting your son, you're
No, I mean, it's true to scientists.
okay, so it's true. Time thought for reading everything.
Yeah.
And then submit Q&A, etc. etc. is decide how you want to yes. Okay, I know. I just like don't rush her. There's something for you. All right, I'm gonna take some more questions in a second. We'll talk about this. Okay. All right, and back to me. This one's super duper easy. What do you notice is happening? There's a couple and another couple, and then they. Well, so A and B are together, and X and Y are together, and then who does A get with? Y is A, which is the cation here, getting with Y. Because that's the anion. And I know it's the 21st century, but in chemistry, we have to have opposites attract. Okay? So, A and Y, and then who gets together? X, because X is the cation, and B is the anion. All of these things are ionic, so if everything's ionic, you always have cation first, anion second, and you always cross charges, okay? Because I will haunt you in your dreams, you don't crisscross charges. You see me. It's serious. Okay, so as you think about that, take your cation, put it with the other anion, and then you will have to consider precipitate rules. So I'm going to show you where that is on your blue sheet. So right next to the activity series, there's a little table over here that says like soluble and insoluble. You've seen that here on the upper left-hand side. It says solubility rules. So you will get this. You have to know how to use it. Okay, so let's start with just writing double replacement reactions, and then we'll use the rule. All right, let's go. Crew. So I'll talk about that in a second. All right, so okay, let's do the example first, and I'll come back to that. Silver nitrate and sodium chloride. What is silver nitrate, Cassandra? Silver nitrate.
Oh yeah, AG.
AG.
N23.
I'm going to put parentheses there for clarity's sake for us, okay? Everybody put silver nitrate, and underneath it, put a positive sign and a negative sign so you understand the cation's first, anion is second. Avery, sodium chloride. Na for sodium, and those happen to all have a 1 plus and 1 minus charge. It's okay. Chemical physical change poster bell. So everything here at a +1, -1 charge. It just happened to work out that way this go around. Sodium chloride done. Positive, negative. Underneath those, you recognize cation and anion. Isabella, who is silver going to get with? No. I know it's 21st century. Opposites attract. Silver and chlorine. Okay, so we're going to make silver chloride, which happen to have a plus. Because remember, silver is number 1. Okay, and chlorine is a -1 charge, so we crisscross those charges. And then Ishmael, who does sodium go with? Sodium's going to get with nitrate because opposites attract again. So I'm not writing nitrate sodium because, like, let me just write it for you. Doesn't that look ugly? If it looks ugly, it's probably wrong. Okay, you're going to start to recognize what things are, like, abnormal. Like, I've never seen that before. If you've never seen it before, it's probably not right. Okay, so sodium and nitrate, each of those carry a 1 plus and 1 minus, so we're good here. Is it balanced? Yep. Okay, so that's a double replacement. This is basically like couple want to just take a break and they try another couple that's on the break too, and yeah, they make new stuff. Okay, so sometimes this is really bad though. Okay, so occasionally that couple, like silver chloride in this case, I will tell you, silver and chlorine, they just have to stay together. So sodium and nitrate are not going to get their previous partners back. So silver and chlorine stay together, and I'll tell you why. It's because of the solubility rules. Right here. Okay, so the things that are soluble, what is soluble? What do you think it means? Okay, so it dissolves, aqueous, stays in solution, something like that. What do you think insoluble means? So no aqueous. So doesn't dissolve. So if you don't know what insoluble and soluble means, there's some this little helpful guides for you. But generally what we write down when something's insoluble, we just put PPT. What does PPT mean? Precipitate. That means it forms a solid. That means it's clumped together and will not pull back apart. Okay, so here's the rules. These rules are really similar to what's on your paper, except I like these better because they're just more clear. But if you look in the soluble category, what anions are always soluble? Bradley, what's the first one? Look at your rules. You're not just doing this from your brain. What's it say? All?
Chloride.
No, we're looking at soluble.
That's nitrate.
All nitrates are soluble. What next? All acetates are soluble. What's next?
Ammonium.
Ammonium, NH4, 1 plus, are soluble. What's next? In group 1.
Salts.
Group 1A, so group 1 metal. So if you have any of nitrates, acetates, ammonium, or group 1, like, lithium, sodium, potassium, and so forth, if it's in that compound, that thing is soluble. We write aqueous next to it, call it a day. Now, there's a couple of exceptions to these. So if you go to the next bullet, it says all chlorides, bromides, and iodides are soluble, except who? Silver, lead, and mercury. Silver, lead, and mercury. Those are called the heavy metals. And heavy metals just generally don't work really well in aqueous solutions, so they tend to precipitate out and form a solid. So, what do you notice was on my example we just wrote down? Ag, okay, so we saw that suspicious character silver. Originally, silver was with who? Right, you just wrote this down. Nitrate. Okay, so since silver was with nitrate, nitrate's always soluble. Put an AQ next to where you wrote silver nitrate on our example you just wrote down. Write AQ next to silver nitrate. That means aqueous, that means soluble. But then we did the whole double replacement and we got silver paired with who? Chloride. Still, silver's a suspicious character. And then you look at your solubility rules, you're like, oh, chlorides are soluble, and then go, oh, except with silver. So chlorides are always soluble, except for silver, mercury, and lead. So here we're going to put PPT, as in precipitate, next to that to show it's actually precipitating out. It's making a reaction happen. It's forming some sort of unknown solid. So that's how you're going to use the solubility soluble rules. So next to here, I told you guys to write AQ and then PPT to represent a solid precipitate. So then what do you want to tell me about this nitrate over here? Sodium nitrate. So soluble or insoluble? Always soluble, right? All nitrates are always soluble. Put AQ. And then what about chloride here with sodium? It is soluble because it's chloride with a well, anything ionic is called a salt. So I'm going to say group 1A specifically. Group 1A is always soluble. So basically we're going to see a clear liquid get together with a clear liquid, and then boom, we're going to see this white solid pop out of solution, and then and like a liquidy clear thing. So we can see that reaction happen actually. All right, let's do the next one. Lead to nitrate and magnesium fluoride. Write out your reactants, do your double replacement. Shelby, give me some lead to nitrate for me. Formula. Lead. PB, nitrate. Okay, so lead to nitrate. PbNO3. Say again? 2, you need to crisscross that charge over. Good. All right, so Jacob, magnesium fluoride. And where's the 2 coming from? Magnesium charge. Good. All right, so William, pick up from here. Give me the first product you want to make. PB and? Well, and F, right? So we're going to make lead and fluoride come together, but tell me what the formula is and why. Okay, so he re-crisscross charges. He didn't just pull the charge or that 2 over with him. He said PB has a 2, fluorine has a 1 crisscross. So don't forget, you always are crisscrossing charges. So PBF2 is good, and then Will, tell me the other product. Magnesium gets with who? Nitrate to make what? Beautiful. And that 2 came from magnesium charge. You guys are doing really good. A lot of you guys are on crisscrossing charges. Okay. And it happens to be balanced because the 2's kind of fell in the same places. All right, so now solubility rules. All nitrates, no matter what it's paired with, are soluble. What do we write next to that? AQ. So put a little AQ next to the lead 2 nitrate, and a little AQ. It's like an extra subscript is really what it is, but I don't have enough space. So AQ next to the magnesium nitrate. Now fluorides happen to not really be on your list because you got chlorides, bromides, and iodides on your solubility rules. Fluorides are very similar, but they act a little different. That's why it's not on there, right? Is there fluoride on there? All right, sorry, there's fluoride's not on this one, I think. Yeah, sorry, fluoride's not on this one. What does it say for you guys? The same rules as everything else? Okay, there we go. So everything except for group 2 and? Okay, so in this case, magnesium, which is in group 2, should be listed as PBT. Okay, so we can either write PBT here or a downward facing arrow to say it's a solid, it falls to the bottom of the test tube. That's what the downward facing arrow means. And then lead to fluoride, same story. Fluorides are all soluble except for group 2, and then the lead in this case is our PBT here. So we'd actually see that reaction happen. We'd see this new solid fall out of the solution. And that's kind of like the interesting part of these reactions. All right, I got 3 minutes with you. I'm going to show you the combustion general guidelines, and then we'll do some more practice with that later, okay? So combustion's our last style. So the single and doubles really aren't bad. It's just you need to know how to use your tools that are in front of you at all times. It's just you practicing with them to feel comfortable. I'll do some more of these with you guys later too. All right, so this is your general rules for combustion. If you see O2 as a reactant, by golly, it is a combustion reaction. So write down your general rules for yourself, and then I'll have you guys talk about it. So you may have heard of combustion. Maybe you didn't think that it was actually about one of the reactants. You maybe thought about like gasoline or some sort of oil that you're burning. But actually combustion means react with oxygen. Anything can react with oxygen. And these are two of those examples that are very common. You can actually have combustion of a metal. What does this kind of look like though? This first example. What other type of reaction? Synthesis. It looks really similar to synthesis. So it's not all that new. It's just actually identifying oxygen as a component. And then combustion of hydrocarbon down here, this is something like gasoline or propane or a lighter with butane in it. We're going to talk about nomenclature later. Okay, you guys trucked through today. Thank you. I wanted to give you a chance to review synthesis and decomp because that was like 4 days ago, 3 days ago. We will finish a little bit more of this in intervention, specifically examples. Okay? So make sure you have your notes for yourself. Your job is to finish some more problem set 11. Finish some more problem set 11, and I'll give you guys your lecture notes during intervention time. Tomorrow we have a lab. So if you have clothes to shoes on, you are good for the lab. Do not wear sandals. If you have sandals, bring in some extra shoes that you don't mind wearing in the lab. I'll hand those back. Thanks. Synthesis takes 2 and 2. 1. Decomposition takes 1 and 2. 2. Single replacement does 1 switch. Double replacement, 2 switches. Bye. Alright, so who wants to be here during that time? William? I'll see you. Yes.
For the project, if I'm doing the rare metal, like